welcome. Let's try to solve another Leetcode problem. 1691, maximum height by stacking cuboids. So for this problem, we are given several cubics, and we just need to stack them together, and we want to find the highest height of the stacked cuboids. Yeah. So we need to meet the conditions. Width gonna be the width I gonna be less than or equal to width Z, and the less I gonna less than or equal to less Z, and height I gonna less than or equal to height J. Yeah. So we're gonna rearrange any cuboid's dimensions by rotating it to put it on another cuboid. So this means we can rotate it. So for example, I'm gonna draw a two-dimension cuboid. So for example, this is one, and this is another one. So if we stack it like this, definitely the height is not higher. But what if we stack it like this? So we're gonna turn it to 90 degrees, and this one similarly we're gonna turn it to 90 degrees. So definitely it's gonna be higher. Yeah. So this is why we can turn it and make it higher. Now we're gonna turn the two-dimension problem into a three-dimension problem. So let me just make a drawing of three-dimension problem. Yeah. So yeah, it's gonna be really interesting. So we have one cuboid. Yeah. And then we're gonna put something inside. Let me just make a drawing like this. We just put this cuboid inside this big cuboid. Yeah. So if we put it inside, and if we want to stack it higher, so the greedy idea is that we can still sort the length, width, and height. If we sort it, definitely we can find the highest one. So for example, this is going to be the highest, because if we turn this cuboid inside to any degrees, like 90 degrees to x coordinates, y coordinates, or z coordinates, it doesn't matter. It will still be inside if it meets the conditions. Yeah. So this means we can still turn it. If it is like this, it is not okay. So we're gonna turn it. We're gonna turn it like this, and then we're gonna put it here. We're gonna stack it up here, and it's gonna be higher. So this is the greedy idea. So this means for the first step, according to the greedy idea, we're gonna sort it according to the length, width, and height. And in this way, we can always find the height. So for the third dimension, it's going to be the height, and for the first dimension, it's going to be the length, and then it's going to be the width and height. And then we're going to use the longest increasing subsequence to find the height, and this is going to be easier to solve. Yeah. Now let's just use this idea to solve the problem. Yeah, so just imagine if you can put a cuboid inside another cuboid. Just use your imagination. Yeah, if you can put it inside, you can turn it to any kind of 90 degrees, to any directions, it doesn't matter. And then definitely you can find the highest height if you can put it inside. So this is the idea. Yeah. Now we're going to check all the cuboids. So for C inside the cuboids, we're going to sort it. Yeah. So for the third dimension, say it must be the height. And after that, we're going to sort the cuboids. So the cuboids.sort. Yeah. So we're going to sort it according to the first dimension, which is going to be, yeah, we can name it anything, width or height. So we're going to name it as width. So for the first dimension, it's going to be the width. So we're going to sort it according to the width. Now, we're going to use the longest increasing subsequence to solve the problem. So for I, let's find it. So for I, width, length, and height, enumerate the cuboids. So for here, let's just use W1, L1, and H1. Yeah, and for J, in range let's just use enumerate. So for j, here we're going to use a w2, l2, and h2 in enumerate cuboids to I, but I is not included. Yeah. Now we're going to check it, but we didn't define the function. Let's define the dp function. So for here, let's define f, it's going to be 8 for w, l, and 8 inside of the cuboids. This is just a template of the longest increasing subsequence, and we can directly check that. So the condition is that if w2 is less than and equal to, yeah, this because we sorted according to the first dimension, it already meets, and we're gonna check the second. So if L2 less than equal to L1, and H2 less than equal to H1, so we're gonna update it. Yeah, so Fi gonna be the maximum of Fi with Fj plus the height. Here the height is gonna be H1. So finally, we're gonna return the maximum height, which is gonna be the maximum of f, because this function we defined it as the highest height at each position. Yeah, so we're gonna find the maximum. Now let me just run it to check if it works. As you can see, it works. Now let me just submit it. Yeah, as you can see, it works, and it's pretty fast, and the time complexity is n squared, because here we have 2 for loops. Here is just a sorting, it is okay. This is n log n, but here is n squared, and n is 10, and n is just 100. That is why it works. So this is a n squared time. Yeah, I think the only difficult part is that how can we think about this kind of greedy idea? Actually, we can prove it. So the edge case is that maybe you think let's just find maybe 3 numbers. So let's just find 2, 3, and 5. We sort it, and another one we're gonna sort it as 2, 2, and 4. So definitely the height is gonna be 5 plus 4. It's gonna be 9, because we can stack this one over this one, because 2 is less than or equal to 2, 2 is less than or equal to 3. It is okay. Yeah, but what if this is not 4? This is 6. If this is 6, it doesn't meet the condition, because all the height is going to be less than or equal to this height. This 6 must less than or equal to 5. It doesn't meet this condition. Maybe you think, why not? Why not I turn it? If I turn it, maybe 2, 6, and 2. But even this 6 doesn't meet the highest 5. Definitely this 6 cannot meet this second highest 3. Definitely it doesn't meet the condition. So this is why we're going to sort it according to the width, length, and height. Yeah. I think that's all about it. Thanks for watching. See you next time.